So we are dealing with the fourth problem in this series, and the fourth problem is stating two positive charges q1 and q2 are located at the points with radius vectors r1 and r2. Find a negative charge q3 and a radius vector r3 of the point at which it has to be placed for the force acting on each of the three charges to be equal to 0. So what is important for this problem is that we need to understand that all the three charges are in equilibrium, and we are provided with the position of the two charges. So this is problem number 3.4. So if we begin with this problem, the first thing that we do is we construct a coordinate system. So we are considering an xy plane, something like this, and over here we draw the position of the two charges that is given to us. So this is r1 vector where the first charge is placed, r2 vector where the second charge is placed. So over here a charge q1 is placed at position r1 vector, and let us consider the charge q2 is placed at r3 vector. q2 is placed at r2 vector. So these two locations are marked in the problem, and both the charges are positively charged. So if we draw a line joining these charges, then the first thing is clear is that the third charge will definitely lie on this line, because the electrostatic force of interaction will act in the line joining the two charges. So these charges are going to repel each other. So the first charge is going to experience a force due to the second charge. This is F21, and the second charge will experience a force due to the first charge F12 vector. These two are equal and opposite in nature. So the third charge which we are discussing must be placed somewhere here, which we are calling as minus q3, and this charge must be placed at a position vector r3, where we can say that r3 vector is somewhat like this. So the distance between the first and the third charge, we are considering this as a, and the separation between the third charge and the second charge, we are considering this as b. So over here we can say that the first, second and third charge are having a ratio a is to b division between them, and a section formula can be applied for valuation of the position r3 vector. So if we apply that formulation, we can directly write that r3 vector can be written as a times r2, b times of r1 upon a plus b. So this is the, using section formula we can write this expression for r3 vector. Now since this is a negative charge, it is going to experience an attractive force from the first charge. So the first force that we identify over here is F13, and F23 will be in this direction, and these forces must balance each other for the equilibrium of the third charge. So we are writing the expression for equilibrium of the third charge. For equilibrium of charge q3, so we can say that the forces must balance, or the electric field must balance. So we can write the expression as k q1 q3, and the separation between them is a square, and this is equal to k q2 q3 and the separation between them is b square. So on solving this one we obtain that a by b, so a by b can be written as root over q1 by q2. So this is a very interesting result, as this result will be helpful in evaluation of R3. So over here we can say therefore R3 vector, which we have already written as a R2 vector plus b R1 vector upon a plus b. So if we divide by b, we can write it as a by b R2 vector plus R1 vector upon a by b plus 1. So if we substitute the value of a by b over here, so we get R3 vector as a root over q1 R2 vector plus root over q2 R1 vector times or divided by root over q1 plus root over q2. So this is the first answer which we are looking for, that is the position of R3 vector which the problem has asked us to evaluate. And the next is to calculate the value of the charge q3. So for calculation of charge q3, now we are discussing equilibrium of the first charge. We can also discuss equilibrium of the second charge. So on the first charge, a force will act over here due to interaction between the third charge and the first charge. And similarly, there will be interaction between the second charge and the third charge, which will create a force in this direction. So these two forces, that is F21 and F13 or F31, must balance each other in magnitude for equilibrium of the first charge. So we are writing for equilibrium of the charge q1. So for equilibrium of charge q1, we can say k q1 q3 by, now the separation between the third charge and first charge is a, so a square, and this force must be equal to k q1 q2, the separation between them is a plus b, so a plus b square. Again we will use this expression that a by b can be written as root over q1 by q2. So k and k cancel out, q1 and q1 cancel out. So from here we can say that q3 is equal to q2 times a square by a plus b square. And if we substitute the value of a by b, so we get this value as minus q1 q2 upon root q1 plus root q2 square. And the third charge must be a negative charge. It is already mentioned in the problem as well. So this is the solution for calculation of q3 and r3. So we have also discussed this very important result for the 3 charge equilibrium case, where charge 1, 2 and 3 are in equilibrium.